Okay, so a warm welcome to everyone tonight. So big thanks to Erlang Solutions who've sponsored this event for the venue, the food and the drink, and some small announcements as well. Codebeam San Francisco, it's formerly Erlang and Elixir Factory San Fran. That's coming up in March. We've got some keynote speakers who are announced. So we've got Kostas Sigonis and Richard Cook, and more speakers are due to be announced shortly. And also remind you about ElixirConf EU in Warsaw in April. So the keynotes there are Jose Vadim, Chris McCord, and Vadna Wu, who I thought was going to be here tonight as well. And we're also hiring, so you know. That's it. Alright, and that's it. Over to you, Mariano.
Thank you. Okay, hi. I'm Mariano Guerra, and this talk is called Building Distributed Applications, Riak versus Partisan. I decided the title before writing the talk, and it was a hard challenge. I'm that guy on Twitter. I'm a co-founder of that company. It runs Erlang on the backend. Check it out. And you're at the Erlang Meetup, and it's London, and it's 2018, just in case. So, some philosophical questions. Who are we? How do we share knowledge? How do we communicate with someone? And who is responsible for this? These are questions that every node in a distributed system usually asks himself, and questions we have to reply or answer when we are designing a distributed system. So let's explore like these two systems, Riak and Partisan, kind of in terms of these questions. So first, comparison. I may introduce them just in case you don't know them. Riak is a framework that allows developers to build distributed applications using a pattern known as the Dynamo-style architecture defined by Amazon in a paper, which I will mention later. And it's the core of Riak. It was extracted and exposed as a framework. It's used quite a lot in many projects. And it's a really cool, powerful, and easy way to get started building distributed systems, getting all the complexities out of the way, as long as your problem fits the pattern of Dynamo. Otherwise, you will have a hard time. On the right, Partisan, it's a newcomer, newer than Riak. It was built by a team of people, mainly you may know Christopher Maplejohn from LASP, because they needed something that would scale to more nodes than what distributed Erlang allows, which is between 60 and 100, which usually is okay for almost every single developer in the world, but they are trying to do what they call planetary scale systems. So they wanted an underlying platform that would allow them to scale to thousands of nodes. Right now, I think the benchmarks, they run between 1,000 and 4,000 nodes already. And for that, they need to change the basic part of the cluster membership for reasons we will see later. Right now, Partisan is used mainly for LASP, a project which is built by a group of researchers around Europe, I think, mainly. But you can use it for your stuff, and today we will see how. And the comparison, I try to compare them because, as somebody here pointed already, it's hard to compare. But I found a way that almost fits. These questions I mentioned, who are we, is what's called cluster membership, which is who are the members of a cluster, who are alive, where are their IP port and stuff like that. Then how to communicate, how to share information. But also a simpler one is how do I send a message to this other node, which are two different things, and one is solved by this layer and one by this. And then on top is where the similarities end, which is why Riak is more of a framework and Partisan is like a baseline for distributed systems. But we will see how can we make it similar. in general terms, we have the membership layer at the bottom that provides point-to-point communication also, just cluster membership, members of the cluster. But since it knows who are the members, it can send messages to the members. Then on top of that, we build the gossip layer, which is broadcast communication. I want to share this information with all the nodes in the cluster. How do I do that? Then you have the gossip layer. And on top of that, you can build two different parts. Metadata, which is you need to store some information about the cluster itself for your application and for running for your problem and for general stuff like permissions, users, groups, or more ephemeral information like metrics and usage by user, for example, for rate limit. And then the question of who is responsible for this, or in another way, where is this, is provided by routing, and we will see how can we solve those. So how can we make them more similar? So let's go back. You can see here, this is the gossip layer of Riak Core. For historical reasons, from what I've learned, there are two gossip implementations of Riak Core. One, the new one, Plumtree for Riak Core metadata, which was introduced in Riak 2.0, I think, and it's the new stuff based on research and papers and stuff like that. And the gossip, the Riak Core gossip is the legacy, which works. That's why they don't touch it. Which is used to gossip the ring, which is a structure we will see later. So how can we make them similar? Well, first, just use Plumtree here because they are two gossip implementations. They do the same. So we could make the initial two layers similar as long as you choose distributed Erlang in partisan. And then we could take the top layer from Riak Core and put it on top of partisan because it only talks to Plumtree. So we could make them similar. We will see today how far can we get. So let's start more into detail. The talk will be a little bit of theory to understand what I'm going to show you. References to research, but you will have to read them yourself. And a demo with code and all working stuff. So let's start with membership. Riak Core uses distributed Erlang, which comes with Erlang. You already have it if you run an Erlang node. The definition, loosely connected nodes in the sense that it waits until a first reference to another name in another node. When you do spawn of a module, a function, and arguments on another node, it will try to connect to that node. Or if you do a net admin ping to that node, then you establish a connection with that node, and it's how do you say? Bidirectional and transitive. Yeah, it's there.
I was reading this.
Yeah. You can disable these transitive connections passing the Erlang VM, the connect all false. Whenever a node disconnects, either because it goes down or because you run disconnect node, it gets out of the cluster, it gets removed. And the nodes are connected all to all. Whenever one node connects to another one and joins the network, the cluster, every other node will have an active connection with that one. That's why distributed Erlang is so transparent and easy to use, and easy. You don't even have to think about it when you use it. But when you have all-to-all connections, then at 60 or 100 nodes, you have 5,000 something active connections, and all of those connections are sending heartbeats between them. So as it grows exponentially, then you start having problems. And how much it scales above 60 depends on the workload you're running, but usually it's mentioned between 60 and 100 where you can scale. If you have seen the EPMD process and you try to kill it and it doesn't die, it's because it starts with any Erlang node and provides a mapping between the node name that you have and the host and the port where that node is. You can see all the nodes in your cluster as long as they share the secret cookie running the nodes function. There are special kind of nodes called hidden, which are nodes that when they join, they don't connect to every single node. If you want to connect to a node in a cluster to do some operations, some management, or to gather some metrics, you don't want to actually join the cluster. You just connect with the hidden flag, and you can list those nodes with nodes hidden or nodes connected. So that's the distributed Erlang membership implementation, which is the one that Riak Core uses and almost every Erlang project uses. So since this project is a research to build bigger distributed systems, they needed to implement their own. In Partisan, the membership layer is configurable because they want to test different scenarios. The default is distributed Erlang, so if you can use Partisan with distributed Erlang and you get what you got from Riak Core, that's how you can make it really similar to the two building blocks of Riak Core. Then you have other three. Hyperview, which is the interesting one. Static is you specify the cluster in the configuration. You tell the nodes and the IPs and the ports in the configuration, and you will never change. And another one called client server, which I haven't researched, but it sounds weird. I don't know how that works. I don't know. It sounds like a Snowflake, like a 2 or more levels of servers. I don't know how it works, but I like Hyperview. You will notice. This is the Hyperview is the one you are going to use if you want to have clusters above what distributed Erlang supports. Yeah, I couldn't see it here. This is the paper for Hyperview. It's really readable. There are papers that are not easy to read. This one is really easy to read. I like it a lot. And go and check it. The section 4 explains the algorithm. If you want to skip everything, go to the section 4 and it's explained there. I will go over a little bit. It has each Erlang node has two views: the active view and the passive view. Active view and passive view are sets of nodes. The active view is nodes with which the current node has an active connection, and whenever it goes down, it moves them to the passive view and takes another one from the passive view and moves it to the active view. And whenever this node receives a message, it broadcasts that message to all the nodes in the active view. And this algorithm assumes reliable transport protocol like TCP. And to calculate how many nodes you will have in your active view and how many in your passive view, those are the formulas: log n plus c and k log n plus c. For c equal 1 and k equal 6, which is what the people in the paper use, and a network of 10,000 nodes, each node on the network will have 5 nodes in the active view and 30 nodes in the passive view. And as I said, active connection on all the nodes in the active view. Every time you receive a message, you forward it to every node in the active view. If the connection fails or gets disconnected, that node moves to the passive view and another one is promoted to the active view. And periodically, each node connects to a neighbor and shares his view of the nodes it knows about. Of course, you keep a limit of how many nodes you have in the active and the passive, and this is calculated by priority. For example, if a new node joins, it has more priority because it doesn't know about anybody. So you want to be friendly and make it come to the cluster. And yeah, and it shares that. So the other question is, how do I communicate with someone? In Riak Core, since it uses distributed Erlang, just send bang or gen server call and stuff like that. It works because every node knows about every other node, so it just works. You don't have to change anything. Of course, the framework provides abstractions on top, which we will see. But if you need to have a gen server register with a name in some node and send it a message, it will work. In Partisan, we said that the membership is configurable and you have 4. On 3 of the 4, distributed Erlang, static, and client server, I don't know client server, but every node can reach all the other nodes. But on Hyperview, you may have 2 nodes that only transitively see each other. So you cannot send a message to a node. You have to use what Partisan provides to send it, because that message may hop between more than one node to reach the destination. So you use the peer service forward message, the node name, the remote PID or the register name and the message, and it will reach there. Now we are on the third level, which is who is responsible for this. And in this case, we have two different use cases. Metadata, which usually is spread, all the nodes know about all the metadata. It's small data in that sense. It's not your main data store, but like users and groups and permissions and stuff like that, and configuration. And routing, I call it routing, which is a request lands in a node and how it knows which node or which server is responsible for handling that request. For example, if you get node 1 receives a put on a key and node 2 receives get on that key, you expect the get to the same node than the put, otherwise you are not going to get the response. So to answer this, the who's responsible for this, the Dynamo style architecture is the one used by Riak Core, which is a paper by Amazon, which also is really readable. So I recommend you to take a look. And the famous ring. Basically, you have n nodes. For example, here 4 nodes, and you partition a ring, which goes from 0 to 2 to the 160 in a number of partitions. In this case, 32, and assign each slice of that range of numbers to one node. And you take care that not every single neighbor is not the same node. So for example, if you say you hash a key and you land here, and you get the 3 partitions, the 3 next partitions, then you will land on 3 different nodes, for example. So this is a way to partition and replicate data and be sure that you're landing on different nodes. Of course, if you ask for 5 partitions and you have 4 nodes, then eventually you will get the same. But usually n is 3 for small service, for so small customers, or usually both. How much is the usual React W? 3?
Depends. Some people are using like 7, 9 and stuff, but generally speaking, it's just 3. Can't say.
So how do we, this that I explained moving my hands and with the ring, which is you get a request and you decide which part of the request is the one that will route the request to the correct node or nodes. So you hash the key, what's called the key, which can be any attribute of the request. It can be the user, it can be the host name, it can be the key, it can be the value, it can be everything hashed. And you land in some part of the ring, and one node is responsible for that, and you can ask for more than one node. I think that's what's called preference list. That's the list part. So how you do that in code? You just hash the key, you ask for the preference list. In this case, I'm asking just for one, but you can ask for more than one. And then you say, okay, send the command. Command can be, that's what your application does. If it's a key value store, it will be put, get, or delete. If it's a pub sub, it will be pub or sub. And then the module that implements the logic. So that part was the routing, which is who is responsible for handling this request. But the other side is, how do I gossip information? Gossip is the term used in the papers, which is one node, I add one user on node 1, and how do I make sure that that user, new user, is spread to all the nodes, so now every single node can authenticate that user. I could implement users and partitions them, so I could have one user only in some nodes, and then use the routing to decide where to send the authentication command. That's a decision. In Riak, it's used on metadata, because usually you don't have so many users and groups where you need to shard your users and groups. But you can if you want. And for the gossip, this is easy because both use the same algorithm called Plumtree. Well, Riak Core uses it to implement what's called Riak Core metadata. and partisan has plant tree, but doesn't have any metadata, but it's really easy to implement. We will see today how. So what's Riak core metadata? It's a namespace key value store. It's replicated to all nodes eventually and asynchronously. It stores the information in memory and on disk. That means since all the data is stored in memory, you shouldn't be storing like a key value store with metadata because you will use a lot of memory. And also, it only waits for the local write to succeed to consider successful. Then will asynchronously replicate. So it shouldn't be for your critical stuff, only for metadata. This plant tree algorithm comes from a paper called Epidemic Broadcast Trees, which is like a tandem. This paper depends on the eParview paper, or assumes something like eParview for the underlying membership. And also it's really easy to read. I think even the authors are the same, or intersection of the authors. So let's see how plant tree works. Plant tree, when you want to gossip some data, you have 3 pieces of state: the eager set, the lazy set, and the message you have seen. The eager set is whenever you get a request to broadcast something, you will push that data automatically to all the nodes in the eager set. The lazy set is eventually you will say to those nodes in the lazy set, look, I have a new value for this key, but you don't send the data. You say, I have new data for this. If the other node is interested, it will ask you to send the data. So it's more lightweight. This happens after a timeout, and they can be grouped. So you can send many I haves in one request. So how does it work? Imagine you have a 5-node cluster, 1, 2, 3. Each has eager, lazy, and messages. So the node 1 has the node 2 and 3 in the eager set, and the 2, the 1 and 4, and so on. Let's say we ask the node 1 to broadcast a message A with a payload. So what it will do is it will send the broadcast to the eager set, which is 2 and 3. And the nodes 2 and 3, of course, won't return the broadcast to node 1 because the broadcast comes from node 1, but we'll send it to the eager set they have, which is 4 and 5. And now 4 and 5, well, 5 will broadcast to the eager set it has, which is 1 and 4, because 3, it received the message from 3, so it won't send it back. And after that, node 4 sends the message. And then something called prune happens, which is node 1 already has the message A, so it's the second time it receives this. So what will happen is node 1 will say, look, remove me from your eager set. You can see there. Because there's a redundancy, there's like a cycle. I sent something and it came back, so there's a cycle on this graph. So remove me from your eager set, move me to the lazy set. And now node 1 has node 5 in the lazy set because it saw a message from that. After a while, the lazy push, what can happen, imagine the node 3 dies. So node 1 does the broadcast, node 2 does the broadcast, but of course node 3 is dead, so it doesn't process it, and since it's the only one that has node 5 in the eager set, it doesn't send the message. After a while, node 1, which has node 5 in the lazy set, sends an I have, with only the key. It says, I have A, have you seen this? And node 5, since it hasn't seen that message, it adds node 1 to the eager set. So it's like rebuilding the tree. So something bad happened, it was working, the broadcast was working well, which is optimized for where the message arrived faster. But since now it sees that another node says, look, you're on my lazy set and I've seen this message, have you seen it? And it didn't see it. The node 5 thinks, okay, I should have received this message from node 3, and I haven't, so maybe node 3 is dead. So now I will move node 1 to the eager set because I received the message first from node 1. And it said, yeah, I don't have it, so please give it to me. And then it sends the payload. And after a while, node 4 also sends the message, and node 5 adds it to the lazy set because it already saw the message once, so it's not the fastest one. So what Plantry does, it's like a water analogy. It spreads the broadcast to all the nodes, and the nodes start adding to the eager set the nodes that where they receive the messages the fastest. So it optimized for the first flood of messages. And then it heals the tree whenever some nodes die. If they see a lazy message, a delayed message that they didn't see, they think, okay, I should have received this already from other nodes, so maybe they are dead. That's quite smart algorithm. It's really interesting. Read the paper. I'm not really good at explaining it. But what happens if the node 3 gets back? It didn't saw those broadcasts. Depending on the use case and what you're broadcasting, you may be able to wait a little bit and you will get an update on that value, which is my case, so I don't usually care about the active anti-entropy. For example, if you're generating user usage rates every 15 or 30 seconds, and you lose a message, you wait 15 seconds and you get the new value. So you don't need to reconstruct the messages you didn't saw. But in case of if you're storing users and groups and permissions, you want to, if you go down and up again, you want to see whatever happened when you were down. So for this, there is something called active anti-entropy, which uses a data structure called Merkle tree, at least in Riak core metadata, which is, I won't read this because you can read it, but it's used everywhere. In Git, the hash you see whenever you commit something on Git is the hash of all the hashes of all the folders and the files, and for each folder the hash of all the folders and all the files. So you start from the bottom of the tree and start hashing, and then hash the hashes until you get one hash. And then you can compare just that hash, and if it's equal, it means that everything below that part of the tree is the same. And if not, then you have to start going over the tree to see which hashes are not the same. It's used everywhere, even in Bitcoin, so it's hip now.
So it's cool.
Now that's cool. And Riak could get some VC funding. They could remove
It's not crash safe, you're saying.
yeah. Today you may lose money using Merkle trees. This is not financial advice or anything. So how a hash tree works in Riak? In Riak core metadata, it's a structure like this. This is the structure which is used in Riak core metadata, but it applies to almost everything. You have the segments, which are stored in E-level DB, which is really hard to make compile in Windows. By the way, some people tried already. And this is why we cannot have Riak core on Windows, because we need E-level DB for this. The segment hashes are also stored on E-level DB, and what's called the upper hashes are maintained in memory. So the hash tree has three operations: insert, update, and compare. Insert is whenever, imagine these are keys, you update a key and it changes the hash it has. You insert a key, it took me a lot of effort to do that, so I appreciate it. You insert a new key, it gets a new hash. You update one, update another one, and now you have to recalculate the hashes of the intermediate nodes for the hashes that changed. So it like bubbles up until the root changes. The hash of the root changes. So now you can, with one single exchange of one hash and one compare, you can know if you have the same data than any other node on the cluster. So the compare operation is that, imagine you have node 1 and node 2, or node 3 in our example, and node 3 goes down and goes up and says, do I have all the metadata that you have? And it says, okay, let's see, do we have the same root hash? No, so something changed. Okay, let's go one level down. Let's compare these four hashes. Which one changed, the third one. So now let's compare that node, okay, the first one, and here is where on Riak Core it's different. At this point, all the segment is sent, because otherwise you will be doing a lot of stuff. And then there's something called, I don't remember what, but you register a callback and you get calls for all the keys, and then you can reconcile the keys that you didn't saw. So it's really efficient. It's really efficient to check, like no tree goes down and goes up after 2 seconds and checks one hash and knows that nothing changed. Just like comparing a hash. It's really cheap and it's really good to get fast comparing small amounts of data to the places where something changed. So let's try, I have internet, so let's try some demo stuff. Let's see some code for this. So, yeah, I can do this. What if you want to play with this? I will make this bigger. Yeah. Can you see?
Yep.
Okay. I will remove in case I was okay. Let's. I created 3 templates, rebar templates, which set up projects. One for Riak Core, one for Partisan, and one for LASP. And today we will see the Riak Core and the Partisan ones. But the LASP is only Partisan template plus the LASP dependency. It's not more than that. So first you go to, I will add the link later, you clone the template on a folder and then you have it. So you can do, let's see what I did here. River 3 new, that's the name of the template and the name of your project. In this case, let's call it Riak Core KB, and I don't have one activated, so it doesn't work. And so it will create some files and you cd to it and call, it's for the lazy, and for me, yeah. That whenever I want to try something, I want a clean Riak Core project to try it. So you make devrel. What this does is it compiles 3 releases with different configurations, so you can run a cluster on your machine. Because the thing that changes is the name of the node and the ports, otherwise they would clash. I have to learn Docker to not do this anymore, but this works. I will add the Docker thingy later when I read. Because Tristan does Docker with Erlang, I think, so I will steal it from him. So now it's compiling LLDB, which is the part that takes the most. And after that finishes, I can start, let's split this so I can start 3 nodes. So I use curl to activate Erlang because I have many versions. I highly recommend it to you. I have a blog post on how to set up curl and use it, so it's not hard. So now that make devrel worked, you do make in one. You do make dev1 console, in another one you do make dev2 console, in another one dev3 console, and you don't have to memorize it or take notes because it's on the README. So release on the clustering thing, make the rel, the console thing, and now you have 3 nodes, but they are not a cluster, they are just 3 nodes. You have to join them. To do that, you run devrel join. What's this? Where I'm sending this? 1 second. Yeah, it's one. For some reason, I will have to type it. Oh no! This is a problem with having many Erlang versions. So now I'm doing the join, which if you see the make file, it's just 3 comments, but it's easier to just run that. And then you check the cluster status. Yeah. And it will say that you have 3 nodes, and two are joining. And that doesn't mean they are slow. It's that you have to acknowledge the joinings. It's not like join and they join happily. It's like a stage. You first join them, which puts them in the state of joining. And then you have to check the cluster plan, which is what's going to happen. And then you have to commit the plan, which is really thoughtful. You thought about the operators not joining anything to the cluster. So you see something like that, and you make the real cluster plan. You see the plan and what's going to happen. And it will join two nodes, and it will transfer 21 replicas because it's a 64 vnode cluster here. So we are happy with our change, so we commit it. Read the makefile. It's not magic. It's just so you run commands and you don't have to copy paste a lot. And it will start joining them, and you will see the messages there joining, from joining to valid, from joining to valid. And you see the real status, and it starts transferring. It starts a process and starts transferring one vnode, and when that vnode transfers, it starts with the next one. And so it's when you're transferring a lot of data, it's slower, but that's why it's careful and it goes step by step. And after a while, it will be 33% for all of them. And now that we have our cluster, what can we do? Well, if you want to stop, you do that. We can, the ping is somewhere over here. We can ping something. What this will do is, it will hash some random value, so every time you make ping, it will land on some other vnode, and it will reply you with pong and with which partition handled the request. That's by default on the template, because I cannot go farther than that, because I don't know what you're going to build. But let's see how to add a key value store, in-memory key value store with that. So on GitHub, the link is on the slides. I implemented a in-memory key value store using ETS, which is one letter away from being a persistent key value store if you add debts instead of bits. Yeah. And since the cool thing is that if you have a cluster of 64 vnodes, that's his 2 gigabytes. So 2 gigabytes by 64, it's a lot. And if you do a 256 vnodes, then you have a lot of, like a terabyte or something like that. So the difference, I don't know where that's the README. So what do we have to change? We go to the main module, which exposes the API, rc-kvrl, and we add 3 methods, functions, or methods. Get, put, delete. Yeah, sorry, I do many languages. We export 3 functions, and the functions don't do much. They call send to one with the key and the command. That's the command. The command is get key, delete key, and put key and value. And what send to one does is what I already showed in the slides. It hashes the key, because we want to, every time you make a request for the same key, that key should land on the same vnode. We get one vnode to handle that, and then we send the command to that vnode, and we return whatever it replied. And on the place on a Riak core application where you put most of the code is on the vnode module, which is like a gen server with different callbacks. So on the state of each vnode, we store which partition are we, because it's usually useful. And now we need 2 more fields: the table ID, the ETS table. Table ID and table name. I don't know why I have both, but whatever. And we add 3 more clauses to the handle command function. One will match put key and value, and we'll do a nets insert. nothing fancy. The get will do a lookup, and the get delete will do a delete. And since we are nice, we reply with not found if it's not there. And that's all. Now you have a scalable, distributed, dynamo style, in-memory key value data store in like 15 lines of code, and all the buzzwords at the beginning are by a framework that is being used in production by a lot of people.
I guess that doesn't handle all the callbacks for adding additional nodes and removing nodes.
Here, what I'm not handling is the handoff, which is whenever you join a node, we have to move some keys to other vnodes. That's explained on the ebook I wrote called the Little Riak Core book. There's a section where it says how to implement a handoff, but it's the strangest part of Riak Core. The callback for the thing of because you have to do it by small increments. So it starts calling you, and you keep like feeding them and telling them to continue and to keep calling you until you're finished. And when you're finished, like you turn down this vnode and set up this one. And what you do if while you're migrating keys, you get a request for that key on the old node and the new node. So luckily they thought about that for us, but it's still, you have to think about the thing because it's the worst thing. When you say, if I receive a put on a key that I'm migrating, what do? I forward it and I store them and I wait on the new node until the migration is finished and then I write it, or I say, no, I'm busy, forget it, or I store it here. It's hard. But it's not a problem of the architecture, it's a problem of your processing commons while you're migrating data from one server to the other. It's hard. So that's how to implement the key value store on Riak Core, and now let's see how to implement. It will be a gossip-based key value store using Plumtree on Partisan.
Does Plumtree cover the migration of data from one node to another?
Yes and no. Yes, in the sense that it's on all nodes, so it will be everywhere. So that's we were talking with him. What happens when you want to have some data gossip to a subset of the nodes and not all the nodes? There's none. Well, in Riak Core you can do it with the vnodes. You just get end vnodes and you send it there. But with Partisan and Plumtree, and even with LASP, there's no control on saying I want this shard. I don't want it everywhere. And for Partisan, it's the same thing. So you do rebar tree, new rebar template, and it doesn't work, and it creates the thing, and you read the README. I don't know how I'm on time, so I will go on the README. You do the same, make DevRel, three consoles, DevRel join, status. Here is different, it will look a little bit different because the underlying clustering is different. And you can also join yourself. You can list the members, you can list the connections. And the ping here is different. The ping here is tell me the node, because there's nothing on top to do routing or anything. You have to build it yourself. So you can do the ping as long as somebody else decides where that ping should go. And here, where is it? Here. How do you do this requires a little bit more of code because we have to implement a behavior. So we had two functions in this case, set and delete. We could implement more. They call the broadcast handler and say set. First set, so it says locally the value, and then broadcast the value to all the other nodes, and get just does get. And to implement the broadcast handling for your logic, you have to implement a behavior called partisan Plumtree broadcast handler, and it's not really hard. You have to export these functions. What do you do when you want to broadcast data? What do you do when you have to merge data that came from a broadcast? a callback to reply whenever you receive some data, if you already saw that data from the chart we saw. Graft is whenever you didn't saw a message and you want it, and exchange it's for anti-entropy, active anti-entropy, which I didn't implement it here, of course, because it's hard. And you can read the Riak core metadata exchange, and one cool thing you can do, which I think it's on one of these templates, you add recon as a dependency to your project, and you trace the module, and then you trigger a broadcast, and then you see all the calls, and then you can understand what's going on, and then you copy the pattern a little bit. That's how I learned how it works. I did a change on Riak core metadata that you can specify that you want to gossip one key, but you don't want it stored in the disk. And how I learned where to put the code is by tracing and seeing what's going on. And the charts I showed in the slides are basically me trying to understand what was going on Riak core metadata. So you have to implement like a gen server with all these callbacks, and in my case I use an ETS to remember which messages I saw to reply to the is tail. And the merge, I'm really lazy. You can use vector clocks, you can use CRDTs. What I did is I remember which node came, and for each node, when you broadcast, you have a monotonically increasing number. So when I receive something new from you, I check if it's newer from your node perspective. And if it's newer, I merge it, and if it's not, I reject it. That means that you can only broadcast keys from your node, and then somebody has to merge them in some meaningful way. Yeah, distributed systems are hard. But it's like just inserts and gets. It's not really complex, and that will gossip the keys to all the nodes. So you can do the reads locally. You just broadcast the puts. And finally, this is more experimental even. You filled an issue yesterday.
Me?
I think it was you.
Yeah. Let's see.
What I did is Riak, where is it? So I said earlier that to make both really similar. Where is it? We could take. Where is it? I lost it. We could take these two and put them over here. The example I showed you just now is for this. The only difference is that Riak core metadata keeps one copy in memory on ETS and stores one copy on disk for persistence, and it does the active anti-entropy, which I don't. But I showed you the miracle tree thing. And the remaining one to implement will be for the Riak core ring. So what I did is I extracted the Riak core ring.url and all the dependencies, and I implemented a plant tree broadcast handler on top of partisan. I'm really confused myself. So what you can do now is set up a partisan project and use the Riak core ring, the Dynamo style, to route the requests. So how you do it? Right now it's an experiment, of course. And you start the cluster, you join it, like you do with the partisan thing, and then you can transfer nodes. So whenever you join the cluster, for now, since it's an experiment, you have to explicitly broadcast the ring whenever you do a change. Of course, later it will be done anytime you mutate the ring. And then you can transfer V nodes to other nodes. Of course, that's only what this will allow is for you to, on any node on a partisan cluster, to say which node should handle this request. All the migration that you said, all the transferring nodes to nodes that are not the same and keeping them separated and distributed and everything still has to be migrated. But it's possible to extract the ring data structure and gossip it around using plant tree on partisan, which is this experiment. And I don't have to do it live because I recorded a weird thing which is like a screencast for the terminal. So what I do here is I create a cluster of partisan. For me it worked, for you it didn't. I don't know what you did, but it worked for me. Yeah, I tried 3 times and it worked.
Works on my machine.
Yeah, works on my local cluster. And then what I do is, I join. You can print the ring to see what's going on. You can list all the members. So now I join the cluster. So what will happen whenever I broadcast a ring is that the 3 rings that right now are different will merge into one. Because the Riak core ring has a vector clock inside the data structures, so it knows how to merge itself. I didn't have to do that. So it says merging ring from pin 3, and then it received again and it's stayed because I already saw that. Now all the nodes know about all the members in the ring, not in the cluster. So it's 2 different memberships. And now I print the ring, and node A has all the V nodes. The A's are because it belongs to that. And now what I do is I get some indices, the first 2 indices, so I can transfer them. And I broadcast the change, and they received it, and then I print the ring, and you can see a V there. It means that node B has 1 V node there that was transferred, and I can print them in all the other nodes and see that it was transferred there too. So now we can do the routing on top of partisan. It's an experiment, but it's possible.
Have you tried to scale it up and see if it does scale more?
It has like 1.5 hours of development. I guess it doesn't scale. I mean, the underlying technology from the code from Riak Core and Partisan will scale. My glue, I don't know. So that was, I think, a lot.
Could you do something different, and that would be like go right into Erlang OTP and replace distributed Erlang, so it's still all the same calls, but underneath it all it does it where it only connects to a subset. Would that be possible?
Yeah. Well, Riak Core assumes that it can see all the nodes, I think, but you can do hidden nodes.
Yeah.
What I thought at one point was if you do like a 64 vnode ring, and then each vnode has a cluster, a 64 vnode cluster hidden beneath it, and so you have to hop 64 by 64, and well, to the 2, I don't know. You have many nodes, and it's not like 65 by 64 or something like that. No, it's more because it's everybody to everybody. It's a lot of interconnections, but it's many 65, 64 node clusters.
Yeah.
So you only pay the 1 extra hop thingy. It's possible. I don't know.
The other thing you could do is you could make it look like you've got all the nodes exposed to you, but actually you only have a few nodes exposed to you. All the others do go through the routing thing. Imagine the machine thinks it's got 1,000 nodes exposed to it, but actually when you message 900 of them, 1,000 or whatever, they would actually all underneath it or do the 2-hop automatically.
That's what Partisan does.
Yeah, but I mean, if you took the networking layout of Erlang and sort of swapped it over, then you could take any current distributed.
They are experimenting with that. I think
Erlang
the main
SD,
problem.
right?
Sorry?
Erlang SD.
Yeah, but it wasn't merged. There was a project called Erlang SD which was trying to do that, but it wasn't merged. But now the Erlang core team is experimented using distributed hash tables, because the main roadblock I think is global, the global process registry. When you want to, that is the part that doesn't scale, or the part that makes it complex to change the underlying cluster membership without breaking a lot of code. So they experimented using global with DHTs, I think, and I think they have something to show in the next year or something. And it will be...
I don't think it will scale to thousands.
But a couple hundreds, I guess,
Yeah, a couple hundreds,
I think they should announce like a test in 21 or 22.
What's interesting is that the SD is actually, if you go into virtual symphony, and there's a paper from the guys, Ken Burman, and they have something that is very similar to what they're trying to do in SD, and is a token ring of nodes, and it scales to 20,000 nodes. And what it does is you form a cluster, a ring, and there's a leader, and that's a leader for that cluster, but then they also participate in a lower level cluster, and you have like 3 or 4 layers.
Like a skip list.
Yeah. So
nodes.
so it's like a tree, right? So it's or a trie. So basically you have five nodes here in a ring, and one of them belongs to another 5.
Yeah.
Another 5.
Yeah.
And
Because I mean, just got to gossip the whole network. You actually
Yeah.
gossip
Yeah.
amongst the clusters and the clusters gossip themselves. So.
And the cool thing is that if you do some tree or 2-hop structure or skip list, whatever, each like root that handles a subcluster has to know the routing for itself, and then it can know all the other routes. I think, but it depends on the use case. For me, I mean, with Riak Core, I'm already okay. I'm just interested in how to use the other one, because there are smart people working on it, so I can reuse it, and it's interesting. So yeah, there are many ways you could do, like distributed hash table, which there's one by Jasper. I think there's one implementation of DHT. Then you have Erlang. Then you have depends on what you want to do. There are different ways of doing it, but depends on the specific case. Personally, I like the leaderless gossipy thing, but the other ones are really interesting too.
Is there going to be an implementation of partisan for a different language, like apart from Erlang?
Sorry?
It would be difficult to port like Riak Core to a different language because it relies on distributed Erlang, but of course the partisan has its own protocol.
You would need an RPC layer, and then the detecting nodes go up and down.
And a mixed cluster where I don't know, a certain amount is C++ or whatever happens to be, and then other nodes are Erlang.
Well, you could join. You can join non-Erlang nodes to a Riak Core cluster using C nodes or J interface and stuff like
that's
that.
what we're doing.
Yeah.
Is to have Erlang be.
Yeah.
Okay.
You could do it like that, or
But there's nothing that would fundamentally stop partisan
No.
being.
just a lot of code.
Okay. Right.
I guess Amazon. I don't know. Amazon wrote this paper. They had some Erlang, but I think it may be Java what they have. So yeah, you can. There's no like as stable and tested as Riak Core open source. I don't think there's one in any other language.
you have implementations within Cassandra and within.
Yeah. Or you have
No.
this, but for a specific use
Hasn't
case.
Dakar cluster taking quite a bit
I like the
from
cluster,
Riak Core,
Yeah, of course.
Yeah.
Yeah, but I don't think if they have the pattern of
Yeah.
nodes and stuff like that. They take more from OTP than from Riak,
Yeah.
I think. Yeah, the only other one, like distributed systems framework, is Orleans in .NET, which is used, Microsoft uses it in production for video games, and in Azure I think they use it also. But it's a different pattern. It's like a transparent message passing like in Erlang, in the sense that you say send a message to this process and it will arrive, but it also handles the life cycle of the process. So if the process is not alive, it will be spawned, and if it's a while without doing anything, it will be slept and the state persisted, and whenever a message comes. So it's a little bit higher level than OTP, but there's a project on Erlang called Orleans, which is Orleans on Erlang, which is built on top of Partisan, and I think it uses a part of Flask too. So there's a lot of cross pollination in Erlang. That's what the cool thing. If you want to try, like you have Riak Ensemble for consensus, for Paxos, you have Erlang for the Erlang style, you have Riak Core for Dynamo, you have Lasp for Lasp. they invented it, so it's themselves. So you have many different, really well-tested frameworks to try different patterns of distributed systems. And of course, OTP, which already...
One final one. Does it only work on a single data center? You know, would it, if you had 2 data centers on opposite sides of the world, would the latency be too high?
Riak has a specific multi-data center replication, which is just, I don't know what it uses.
It's kind of an asynchronous sort of.
Yeah, it's not like a routing of B nodes, but it does some synchronization across data center. And I think it's data center aware. Like you have per data center clusters and then a component that does the cross.
Partisan, could that be done across a non-reliable?
That's the idea, because they started doing LASP for Machine Zone, which was a video game company, and they wanted it to synchronize leaderboards for video games on mobile. Like you're playing a game and you go to a tunnel and then you go out and you want to synchronize whatever you did and whatever happened outside. So yeah, it's for less slowly, eventually consistent data, in the sense that like nodes can go down quite heavily and eventually it will converge to a state. It's hard. Well, it's not hard, it's more restrictive. The set of operations you can do with the CRDT are really restrictive because they have to be commutative. Like, no matter the order you apply them, they have to converge to the same value. But if your problem fits, yeah, in case you're interested. I implemented because I was thinking, there's no LASP code to read that implements something like something. So I implemented a role-based authentication. I don't know what
Access control.
Access control.
Yeah.
I didn't know what the C was, which is stolen from a little bit from Riak Core security and a little bit from Snarl
from
Heinz.
FIFO.
Yeah. So I just copied the interface, and it uses LASP. So it gossips the users and the groups and the permissions using CRDTs. So you can play with some real use case on LASP on Partisan, and it seems to work. If it doesn't work, it's not my fault because I'm using CRDTs and LASP. I'm using them as advertised, so it should work. And this you just do an operation on one node, and it will gossip and converge on all the nodes, and do the anti-entropy and everything. So you should persist it somewhere. If you read, I think I asked Christopher, and as long as there's one node running, the whole cluster can crash. Eventually, all will get that. But if I don't feel comfortable not persisting, because it will be as long as there's one node alive, it will then later be replicated to all the nodes when they go up. But I would like to persist it, and I don't know how to. If the whole data center goes down and goes up, and then you start lifting the data from the store to the CRDT, if it will generate a lot of conflicts, merges and stuff like that I have to see. But that's for later. So if you're interested, this is like a use case, a real use case on LASP on Partisan. You can play and you can build a cluster and you do the operation in one and you check in the other one that it merged and that it appeared and stuff like that. So yeah, a lot of code. I will post all these links. I have some on the last slide, but not all of them. And so the Riak Core KV and the Partisan KV with broadcast is here. The Riak Core ring on Partisan is here. These are the slides, and I will post that one, the role-based access controller. So I think I'm way out of time. Oh no, it's 1 hour more.
Yeah.
Okay. Well, I'm still out of time, but not so.
No, we've got an hour to go.
Okay, I ran out of stuff to say. Thank you.
Excellent. Thanks a lot, man.